Okay, so we're going to integrate this function here, cosh of z, which is the hyperbolic cosine, divided by this polynomial, which is z to the 4 plus 2z squared minus 3, and with respect to z, and it's on the complex plane within the square S, and S has these corners here written down, which I've now drawn on this complex plane graph with the real axis and the imaginary axis, minus 2i plus 2 real and the minus 2 real. And this is our square, what we're going to integrate over. So where do we start with this integration here? To just integrate this like if it was a real valued function, that would be really complicated with the hyperbolic cosine and this polynomial in the bottom. But with complex numbers, we've got a thing called Cauchy's residue theorem. Now Cauchy's residue theorem is written like this. So on the complex point, so we call that gamma, the integral of this function with regards to z dz, this is equal to 2 pi I multiplied by some number which we're just going to call k. You can use any letter you like for this. And k is basically the sum of all the residues of f of z. So k is the sum of the residues of f of z. Okay, so if we now take this integrand out of the integral and just find the residues, we can then perhaps apply Cauchy's integral formula in order to find the actual value of this integral. Now it's valid because we're going to integrate over this square, which is a closed contour inside the complex plane, and there's no gaps in this at all. It's a solid place. So we can go straight into the residue theorem. So now our function here, f of z, let's just rewrite that down over here. So we're now let f of z equal cosh of z divided by z to the 4 plus 2z squared minus 3. Now this looks a little bit complicated here to try and solve this. So what I've got to try and do is maybe factor it out somehow. So our goal is to try and find the singularities, i.e. when this is valued at 0. So for which value of z that's going to be 0, we'll need to factor it. So let's just put a little arrow here. Just going to look at this polynomial in the denominator. Now we've got z to the 4, a 2z squared and a minus 3. So it's looking quite handy here. We could have a z squared and a z squared as our two factors. So that would lead our factors here. And then with a minus 3, we're going to have a plus 1 and a minus 1. So plus 1 and a minus 3. So if we multiply this out, we should get this. So plus 1 and a minus 3 will give us minus 2z squared. So therefore we need to change the signs from a minus and this one to a plus. So now a plus 3 and a minus 1, multiplying these with the z squared will give us a 2z squared. Minus 3 plus 1 give us a minus 3. Z to the squared, z squared give us z to the 4. So now we've got this split up into two factors. But it's still not finished. We still need it in the form of something like z plus alpha, for example. But we've got z squared. So the residue theorem is still not going to be valid at this stage. So now we need to factor out each one of these again. Now z squared minus 1, we know we can do that. That gives us z squared plus z squared equals plus 1. So if I just do this, z squared equals 1, z equals plus or minus 1. So that's pretty straightforward for this side. So let's just write that in there. z plus 1, z minus 1. Okay, so that takes care of that. Now what about z squared plus 3? This is looking a little bit more tricky. So z squared plus 3, set that to 0. Z squared equals minus 3. Okay, well, we're in complex numbers, so we can now factor out this z squared equals minus 3. So we can say z equals, well, take the square root of that. So now what we can say is z equals plus or minus I square root of 3. So that gives our solution there to this one. So now we'll write that one as z plus I root 3 and z minus I root 3. So there we go. So now we've got 4 positions there on our complex plane where this denominator could equal 0. So any one of these is 0, that's going to give us a singularity. So z plus 1, for that to be 0, z equals minus 1. So we've got 1 here, so that's our minus 1. Z minus 1, well, for that to be 0, z has to be positive 1. So that's another singularity here. Plus I root 3, so that means this one will be a singularity at minus I root 3. So that's going to be somewhere around about here. So minus I root 3. And then this one, obviously, because it's a minus, that's a plus. The other one is going to be reflected in the real axis. So that's going to be plus I root 3. Okay, now let's rewrite our function here with these in the denominator. So f of z equals cosh of z. And then write down these 4 factors. Z plus 1, z minus 1, z plus I root 3, z minus I root 3. Okay, so now we need to go and calculate all the residues. So we can then find our constant k when we found all 4 of the residues. So we've got 1, minus 1, 1, I root 3, minus I root 3, all inside the square. So we're going to need all 4 residues. So let's start straight away. On the first one, let's go for minus 1. That will make this term disappear. So now we need to put minus 1 into this one. So all the z's will become minus 1. So cosh of minus 1. And then obviously this one makes that into 0, so we cover that one up. So minus 1, that becomes minus 2. And then minus 1 plus I root 3. And minus 1 minus I root 3. Okay, let's evaluate this denominator here. So we've got the minus 2, let's just leave that for now. Now these 2 terms here are conjugate of each other. So what we do know is that when we FOIL the I root 3 with the minus 1s, we'll end up with a plus and a minus, so they will disappear. So we could just concentrate on the first and second terms. So minus 1 times minus 1 gives us 1. And then the I root 3 times that minus I root 3. We'll just go careful on that a little bit, because square root of 3 times square root of 3, okay, no problem, that is positive 3. But the plus I times the minus I, well, we know that I squared equals minus 1. So therefore, plus I times minus I equals positive 1. So then we can leave that as a positive 1. And the I root 3 times the minus I root 3 will then give us a positive 3. So this will then become minus 8. So we'll rewrite this down here again, minus 8. Now the cosh of minus 1 we can rewrite that as cosh of 1 if we like, because remember the cosh graph looks something a little bit like this, basically reflected in this positive axis here. So obviously the -1 and the +1, they are the same value. Okay, so let's write this down here now as cosh of 1. So that's our first residue taken care of. So the residue of f at -1 is cosh 1 over -8. So we'll just call that minus cosh of 1 over 8. So that's our first residue taken care of. So now let's have a look at the next one in this denominator, which gives us a 0, which is z equals +1. So let's try that one next. So the residue of f at +1. So now I'm going to plug in +1 into all of these. So now we've got cosh of 1. 1 + 1 is 2. And then this one disappears into 0, so we ignore that. And then we've got 1 + I root 3, 1 - I root 3. Okay, so as before, we got complex conjugate here. So we know that this then becomes cosh of 1 with 2 times, 1 times 1 is 1, no problem. Then the I root 3 and the minus I root 3, from before we knew that that becomes +3. So this residue now is cosh of 1, 2 times 1 + 3, which gives us 8. So basically it's the different sign for this first one. So it's residue of f at 1 equals positive cosh of 1 over 8. So that's the first two residues taken care of. Okay, now let's have a look at the next one. It's getting a little bit more complicated now. So now we're on to the -I root 3. So this one here. So this one will be the one that disappears next. So residue of f at -I root 3. Okay, so now the residue here. Let's plug in -I root 3 for all these z's. So now we've got cosh of -I root 3. Okay, now that looks really awkward, but we can use some properties and simplify that up a little bit. Now we'll want -I root 3 in here. This one becomes a 0, so we ignore that, and then a -I root 3 in here for all the z's. So I'm going to write this as 1 - I root 3. And then this one here, I'm going to write -1 - I root 3. And then here, -I root 3 - I root 3 becomes -2 I root 3. Okay, let's have a look what we got here now. So I'm going to leave this one till last. Now I'm going to FOIL these ones. So let's see what we've got here. So I'm going to leave this cosh in here for now. Okay, so 1 - I root 3 times -1 - I root 3. So 1 times -1 gives us -1. 1 times -I root 3 gives us -I root 3. -1 times -I root 3 gives us positive I root 3. And then here, -I root 3 times -I root 3. Well, the root 3's will become +3, and the i's squared will become -1. So -1 with a minus and a minus becomes another minus. So that will end up with -3. Okay, so now we just multiply this by this last term, minus 2i root 3. So these will cancel out. That makes life a little bit easier. And then minus 1 and minus 3, that becomes minus 4. So we've got minus 4 times minus 2i root 3. This simplifies to 8i root 3. So let's put our denominator in, 8i root 3. Okay, now cosh of minus I root 3. Well, cosh of minus I, if we just look at that alone first, I'm going to write that here. Cosh of minus I, this is equivalent to cosine of minus 1 or cosine of positive 1, whichever one you want. And the root 3 here, which is also a constant, that will now stay inside of the cosine. So I'm going to write this as cosine square root of 3. So the root 3 will stay, that's our constant, and our imaginary minus I will give us the positive or negative 1, whichever we prefer. So I'm going to write that as cosine cosine of square root of 3. Now this 8i root 3, I could leave this in the denominator, or I could bring it up top and write this as minus I cosine square root of 3, which is how I'm going to write it. So I'm going to write this now in here. So the residue of f at minus I root 3 equals, so the I I'm going to bring up the front, up to the top, and write that as minus I. So minus I cosine of square root of 3, and divided back by 8 root 3. Now, don't be tempted to try and cancel these square roots of 3. Square root of 3 there is the input for cosine, so just leave that one there where it is. Okay, so now we've got the last residue, which will be the positive version of the I root 3. So now we're going to plug in I root 3 for all of these. So we've got cosh of I root 3, which we now know how to deal with. Then I root 3 into all of these, except for this one, which then becomes the 0, which is the singularity. So that one will be ignored, so I'm just interested in these first 3. So now we've got I root 3 plus 1, I root 3 minus 1, and then I root 3 plus I root 3 is 2I root 3. So we know what the numerator is. We did that in the previous residue. So cosine of square root of 3. Now I root 3 times I root 3. I squared is minus 1, and the root 3 squared is 3. So this then going to give us minus 3. And then I root 3 times minus 1 and I root 3 times plus 1. Those are going to sum together to give us a 0, so we can leave that out. And then plus 1 times minus 1 gives us minus 1. And then we multiply this by 2I root 3. So we can simplify this off. Cosine square root of 3. Minus 3 times minus 1 is minus 4. Minus 3 plus minus 1 is minus 4. Minus 4 times 2 is minus 8. And then I root 3. So minus 8I root 3. Okay, so now we've got a minus I in the denominator, which we can now bring up into the numerator to become a positive I. So now I'm going to rewrite this one here in the answer as a positive residue. So the residue f at positive I root 3 equals I cosine root 3 and then divide that by 8 root 3. Okay, so that's all our residues. So now what we need to do is find our constant k. So let's take all this off the board. We don't need that now. So now what we need to do is sum all of these up. So cosh of 1 root 8, let's put the positive one first. Cosh of 1 divided by 8 minus cosh of 1 over 8. Well, this we can see straight away that becomes 0. And in here we've got I cosine root 3 divided by 8 root 3. And then we're going to subtract I cosine square root of 3 divided by 8 square root of 3. This one also will give us 0. These two will cancel out. So therefore what we can say is our integral over S, our square of cosh of z over z to the 4 plus 2z squared minus 3 dz equals 2 pi I times 0. Obviously our k is 0, so hence this equals 0. Okay, so there we go. That's how we can integrate this function here using Cauchy's residue theorem and Cauchy's integral formula. There we go, all about the residues.